Today's speaker in the experimental mathematics seminar of Rutgers University is the one and only Dr. Z, who will speak about the proof of the Riemann hypothesis, the proof that P is not equal to NP, the Goldbach conjecture, and the irrationality of the Euler-Mascheroni constant. I know you all think that this is an April Fool's joke. I know you may think that I'm a little bit eccentric, even weird, but I don't think you can accuse me of being a full-fledged crackpot who thinks that they have a proof. But I do.
Are you kidding me? I'm dialing in from the top of a mountain right now.
Oh, thanks for coming. Okay.
Just to see Riemann hypothesis. You're telling me it's a joke?
It's not a joke. My point is, people, it's a meta joke. Everybody assumes, like in Agatha Christie mysteries, you have the initial suspect, and usually the initial suspect is never the ultimate suspect. So then it goes to the main suspect, but at the end, the initial suspect, after much more sophisticated thing, he tried to become. So this is a meta joke that this is not a joke. I have full proofs. But unlike most seminar talks, where people brag about their own work, trying to advertise their own tiny, usually, not always, but usually tiny achievements, my talk is purely expository. I'm not an egotist. I'm not selfish. My talks are, this talk is completely expository. The proofs I'm going to mention today are not due to me, but they are not as well known as they should be. So I'm going to review these proofs, time permitting. And my pet peeve is somebody who says it's not yet known whether the twin prime conjecture is true, although they got pretty close. It's not yet known whether the Riemann hypothesis is true. It's not yet known whether P is not equal to NP. This makes me so angry. It is known as sure as the fact that I will not be alive in 2,000 years. There is no rigorous proof that I will not be alive in 2,000 years. But I'm almost sure, not almost sure, I'm 100% or 99.999 with 1,000 digits that I will not be alive in the year 2000. So the status of the Riemann hypothesis, the P not equal to NP, and other famous problems are that they are definitely true, and there exist proofs. What people derogatorily called heuristic arguments or plausibility arguments or heuristic proofs are really proofs. So what is nowadays called proof, what the Clay Foundation would give you $1 million for, is not a proof. We already know for sure that the Riemann hypothesis, etc., are true. They want a formal, rigorous, logical proof that is only an artificial game, a fun game, but still a game. As far as a philosophical, epistemological certainty, it would not add an epsilon if somebody like Richard Perlman tomorrow came up with a proof of the Riemann hypothesis that the Clay Foundation would be willing to give $1 million. Of course, he would decline it, but he would be willing to give it. Because, as you know, I'm sure many official proofs that were published in reputable journals, for example, the Annals of Mathematics, turn out to have errors and unfixable errors. And for every such proof that is erroneous, every such erroneous paper, I'm sure there exist 10 proofs that have not yet been detected, erroneous proofs. So my point is that from now on, proof should not be confused with rigorous or formal proof. So as usual, I'm gonna now share. When I teach, I don't use a blackboard, I teach Maple. But for this class, my proofs will all be experimental. And once again, they are not due to me. The first proof for the Riemann hypothesis is due to my great hero, Andrew Odlyzko, a former colleague of Neil Sloan. And the other proof is folklore, is a probabilistic proof. I'm going to give two proofs, not new and not due to me, of the Riemann hypothesis, and two proofs of the P not equal to NP. Once again, none of them are due to me, but they are not as well known as it should be. And this talk is purely expository and a little bit philosophical, trying to make a philosophical point about mathematical certainty. Do not confuse a rigorous mathematical proof with knowledge, whether or not it is true. It's two different things, and they have almost nothing to do with each other. So, Robert, I don't know about how do I share the screen? I don't know.
It should be sort of towards the bottom. Of
right. So screen, sorry. I usually WebEx. Okay, so I use the. Oh, Robert, you see the Maple screen?
Yeah, we see Maple.
Okay, theorem. Let zeta of S be defined by the sum of 1 over n to the power s. S n goes from 1 to infinity. This is erroneously called the Riemann zeta function. But Riemann did not steal it. In the beautiful paper of Riemann that is easily available on the internet, both in the German original and in the English translation, he gives due credit to Euler. This function was defined by Euler. And as you know from Calc 1, or maybe Calc 2, if S is bigger than 1, it converges. So it makes sense. The new idea of Riemann was that S can be complex. It still makes sense with S is complex. And then the same argument from Calc 1, or maybe Calc 2, so if the real part is bigger than 1, it converges. But Riemann proved, using very, very elementary complex variable, that you can be meromorphically extended to a nice, good-looking function that is very easy to compute with computers using the so-called Euler-Maclaurin formula. You can compute it very, very fast. And Maple has it. So let's use Maple to investigate this function. So let's plot. So it's a complex valued function. So let's plot zeta of 1/2. That's IT. It has real part and imaginary part. And what's nice about Maple, you can plot both many functions, in this case 2 functions, at the same time, and see, get an experimental proof. Not due to me. The first 5 zeros were given by somebody called Graham, the same guy I think from Graham Smith.
Do you mean imaginary in the second part?
Yeah, thank you. Robert, tell me if the syntax is right.
Looks good.
Okay. So let's do it from 0 to 20.
I think you need a closing. Oh, okay, you got it.
Okay, thank you. Take a second. Sure enough, the real part is sometimes often the 0, but sometimes they meet. And not only that, they meet here, right between a little bit before 15. So we can zoom in and have, and that's Graham, this due to Graham without computers using the Euler-Maclaurin formula. He found very good approximations. He was a great guy. So you see, and you can zoom in more and more and more, and experimentally prove they exist as 0, the first 0. And Andrew Odlyzko found theorem that the real part, if you of Z sub n, if n is an n0, complex 0, not counting the so-called trivial zeros, is 1/2 for n at least 10 to the power 10, I think. I'm not sure. He also proved the window between 10 to the power 22 and 10 to the power something. Then this is true for so and so many things. So I claim it's implied modulo a lemma that has yet to be proven that real of the n is 1/2 for every n. And let me give you an example of many theorems for which proving it for sufficiently many special cases, even sometimes very few ones, consist a completely rigorous proof. And my favorite example is what we taught our students in Introduction to Proofs things to prove this thing that 6-year-old Gauss he discovered. It's due to Pythagoras, but he discovered, you all know the story, I won't repeat it. So if Gauss would have been really, really smart, even smarter than what Gauss is, he would say, true for n equals 0. Robert, why is it true for n equals 0? What's the left-hand side?
0.
What's the right-hand side?
0.
Very good. Charlie, why is it true for n equals 1? What's the left-hand side?
1.
And the right-hand side? 1 times 2 times 2.
2 over 2.
Very good. This is 1. N equals 2. Let's see. N equals 2. N equals 3. Purity! So this is a class of theorems where both sides are polynomial. So if the polynomial is degree d, in this case, easy to see that it's degree 2. The difference of two polynomials of degree 2 is degree 2. So a polynomial degree 2 is given by 3 degrees of freedom. Oops! I'm very, very wasteful. Occam would be mad at me. Since it's degree 2, you need, so d plus 1. So this is a trivial example, but perfectly, and we don't tell our students this. And a less trivial example is that in Fibonacci, for the Fibonacci numbers, is something called Cassini's identity. That most people think still you need a logical proof. But using the so-called C-finite ansatz, and no offense to the Journal of Integer Sequences that was founded by my good friend Niels Sloan, but now the editor-in-chief is somebody who I'm not very friendly with, has quite a few papers in which such things, similar things, are still proved rigorously. So that's fine to get nice, elegant proofs. But in this case, I don't have time to show you exactly why, but it's elementary linear algebra. For any Fibonacci identity and much more general, it is, if you check it, true for n equals 0, 1, 2, 3. This is suffices, QED. So all we need to prove the Riemann hypothesis is yet another such lemma that you can prove once and for all, yet to be proven. And then it turned out that what Andrew Disco probably worked very hard for nothing. Probably 100 special cases would suffice, maybe more. So this is my speculation. So this is my first proof, modulo a lemma, that is essentially due to Graham and later on with much more data to Andrew Discourse and Terriel and other numerical people who unfortunately do not know whether they have a proof. In fact, Andrew Disco, private communication, told me that he's not quite sure whether it is true or false. So I think that he's being insincere. He's just trying to be interesting or something, trying to be, anyway. Second proof, even more convincing. Yeah.
Can you adjust your screen so that we can see your eyes when you're telling us these things?
Oh, thank you.
Ah, wonderful, thank you.
Thank you. But it's not relevant for sure. Anyway, second proof is even more convenient. Once again, it's not due to me. It's a probabilistic proof. Now in computer science, in cryptology, cryptologists and other places, probabilistic proofs are completely acceptable. We know that you don't need the safety if you can prove it with probability of something, of somebody breaking into your bank account. Probability is 10 to the minus 100. You can be pretty safe. So next proof I like even better because it's much more elementary. You can explain it to a 5-year-old or okay, 7-year-old. Because to fully explain the original statement of the Riemann hypothesis, you have to first take a course in complex variable and analytic continuation, homomorphic integration, and this. But you can explain the notion of prime to a 5-year-old. And you can also, there's something called the Mobius function. Is also you can explain to a 5-year-old or 7-year-old, a smart 5-year-old. So the Mobius function remind you, if thanks to Euclid or whoever, every integer can be written as a product of prime factors. Sometimes it's powers. So if you have powers, it's called S square. But if it is square free, if it has powers, forget it. So reminding you, I'm sure you know, most of you, but it's good. So mu of n equals 0 if n is divisible by a square. In other words, if the powers here, a1, a2, ar, if any of them is bigger than 1, and so it's square. But otherwise, otherwise it is, if it's not square free, it has r primes. So it's a very simple function. And let's look at Maple. Has it Mobius? It's called in Maple Mobius, and n goes from 1. Once again, it's not you to me. I don't know. It's you to. It's folklore. So it's some ren. Oops, sorry. Mobius.
There's a line at the very top that isn't commented out.
Okay. Thank you.
Further up. You have to scroll up, I think.
Oops. It's over. Okay. It's over. Okay. Mobius. And so let's have the first few 1,000 of this. Very, very neat. So you see, it is a 1, -1, or 0. Looks pretty random to me. And it's about 1/3, 1, 1/3 -1, and 1/3 0. So let's call it this sequence P. And it's not too hard to prove that the Riemann hypothesis is equivalent to the following statement, RH. Much more elementary. You don't need complex variable. You don't need anything. All you have to understand what it means to be a prime and what it means to factorize. So random is equivalent, and that's an exercise. Okay, to prove the equivalent, you have to know. But if you didn't know anything about complex variable and you prove this using this formulation, you get the $1 million, I'm sure. Of course you will, because it's in many textbooks, there's equivalent. So the so-called Mertens function is a partial sum of the Riemann, the Mobius function. Sorry, I. So this is a famous Mertens function. Now, the same guy Mertens who invented this function. Okay, let's say let's have the macro to see how it looks. M n goes to ADD add defining the Mobius, the Mertens function. I goes from 1 to n. Example. Let's form the first few values. I goes from 1 to 1. And let's plot it. Let's have a plot. So this is a histogram rather. And maybe I can plot it. So forget about P. This. Plot, sorry. You can plot this. So it's a sequence of points. Looks like a cardiogram. Looks like the Wall Street thing. And let's do a little bit more. So I take why 6,000, but it takes seconds. Give me a second. If not, I'll stop it. Okay, here it is. If you see, it never goes above 21 here and minus 22. So let's divide it by the square root of I. And see what happens. Sorry, maybe 6,000 was too much. Here it is. You see, the largest, when you divide by square root of I, or the largest is 0.4, and the smallest minus 6. And it's amazing that Mertens, more than 100 years ago, with other computers, made the following conjecture, Mertens conjecture. That the absolute, sometimes it's positive, as you see, sometimes it's negative, but m of n is less than or equal to the square root. It was wide open, and some people stupidly believe it, but in around 1980 something, Andrew this go wrong. You had to go very, very far to find a counterexample. Very, very far, but it's wrong. It's still open if this is true. But I think that probably this is also wrong if you go really, really far. But what maybe Mertens proved that RH is equivalent. If you just put an epsilon here for any given epsilon, there exists a constant depending on epsilon, such as this is equivalent. Now, let me remind you the central limit theorem. This looks pretty random. So let's do a control experiment. Let's define a random, a pseudo-random, of course, value generator in Maple. And let's define such a random sequence that looks very much like the non-random sequence of the Mertens function. So let's define some list L, SDQ. So this is, and I want to make it pretty large, so I won't print it out. 6,000. And now let's plot the analog of this, the partial sums. So in this case, instead of MI, you add L bracket J. That's the partial sums. J goes from 1 to I. Robert's okay?
I think so.
Okay, take a second. So, and now I can do it many times. So in this case, it was a bad day. they lost most of the time. But by the central limit theorem, now, so in this case, the Mertens function is even better than random empirically. But I'm sure if you go far enough, it will be almost random. But there's no reason to believe that's the fact that a random square-free integer, whether it has an even number or an odd number of prime, is like tossing a coin. And want to know it's square-free. So for me, it's such a convincing thing, unless God is very, very malicious. And Andrew Lisk and others went with this diagram much farther. And there's no reason to believe it will all of a sudden change and deviate from being like the central limit theorem, only better. Here we see it's 1.5. So, so 5 sigmas usually are to be sure. So this is the probabilistic proof. So once again, is not due to me, but deserves to be better known. As far as I know, quite a few people that are not aware of this beautiful heuristic proof, but I don't call it heuristic proof. I call it a definite proof. It's not a logical deductive proof. It will not give me $1 million, but it gives me absolute certainty that this is true. Now, I also promise you the P not equal to NP, since I don't like the axiomatic method. One of my people that I love to hate is Euclid, who initiated the axiomatic method, and he ruined mathematics and made it into a religion, into a very, very strict, pedantic, minutiae religion. It's a little bit like, I don't want to, okay, never mind. I was going to say, but I don't want to get into trouble, a little bit like Orthodox Judaism, who are very, very strict about the letter of the law. But then Jesus came and he was, and nowadays we have other branch of Judaism, Reform Judaism and Conservative Judaism. And in Israel is a big battle whether who is a Jew. So in this case, that's the analog of the question, who is a Jew? And the Orthodox Jews got very angry that conservative Jews are also now considered Jews for legal reasons. So anyway, that's a little bit analogous. So anyway, let me go to the last things on the agenda, because this is another beautiful proof that gamma's constant, gamma Euler's constant, Euler-Mascheroni constant is called, because sometimes E is called Euler's constant. So let me remind you, it's irrational. It's another proof. Not due to me again. It's due to another person that I love to hate, in addition to Euclid, Cantor, Georg Cantor, who introduced all these crazy infinities that I don't believe in, but he has, you can use his logic, you can kind of use it metaphorically, so you can make sense out of it. Anyway, let me remind you, the official definition that goes back to Euler possibly is a limit, as you know, that I already mentioned the harmonic series, you know, from calculus, from calc 1, calc 2. This diverges, but if you subtract log n, log natural n, you get a number and goes to infinity. But the better definition is in terms of an integral, minus the integral of minus e to the minus x times log x from 0 to infinity. And Maple knows this fact. So here it is. Now let's make digits pretty large. So that's the first empirical proof that it is irrational. By the way, nobody has a proof of this. And in the famous paper or speech of Hilbert in 1900, where he formulated has 23 problems, most of them have been already proved, but not all of them. Before he started listing his 23 problems, he mentioned 2 other problems. And one of them is whether to prove that gamma, this number, is irrational. So the reason he did not make it as part of his 23 problems, probably because he believed that this is even harder. He didn't want to do, he only wanted to state problems that he believed have a chance of being proved. So Hilbert believed that humanity is not ready for this yet. So I call it Hilbert's zeros problems. Anyway, I have a proof, but Hilbert would not agree. So a valve, okay, so again, okay, let's do it again. A valve here. So you get it to many, many digits, thousands. The big number. Now, if we were being rational, you can convert it to continuous fraction. It didn't terminate. If we were being rational, sooner or later it would be the finite. As you know, back, essentially Euclid proved if you have a rational number, eventually the continuous fraction, the Euclidean algorithm will be this. So this is an empirical indication that it goes forever. But this is not yet a convincing proof. And you can make digits much larger. So if it is a rational number, it should be a huge, huge, huge denominator. So my principle is unless theorem, unless it is obviously, unless a real number is obviously rational, it must be irrational. It's a probabilistic proof once again. But first, let's give examples of numbers that are obviously rational. Eric, thanks for coming. Eric, I just want to make sure that you are paying attention, not just do something else. Eric Sandog, what is the square root of 9/4?
3/2.
Very good. So this is obviously a rational number, but square root of 8/4 is not. Okay. Another thing, a little bit less obvious, is the following one: sum of 1 over n times n plus 1. There's an infinite series. Most infinite series are not rational. But this is rational. And this is also rational. Can anybody tell me why is this true? Charlie? Do you take Calc 2?
I did. I'm not recognizing it.
Okay, what about this?
You can make this telescope, right?
Yeah.
Partial
so use
fraction.
partial fraction. You can write this 1 over n plus 1 and more. And this is, it'd be more complicated. It's so-called telescoping series. On the other hand, this simpler sum is famously a pi square over 6. And of course, thanks to Lambert or Lindemann or whatever, it is rational. So both of them are obviously things. Now, remember good old Georg, who proved the two lemmas, number of rational numbers, or cardinality, that's a fancy name for this. Cardinality of the set of rational numbers is what is it? Yotam, what is cardinality of the set of rational numbers?
Cardinality, the number of it's A0, right?
Yeah, so your term, what's the number?
Aleph 0,
Right.
not A0, Aleph 0.
Your term is a fellow Hebrew speaker, so he knows about Aleph. But I'm sure all of you also know. And so you may know the other letter, okay? And now, also, the same good old Georg proved another lemma, kind of the set of real numbers. Real numbers is what? Who can I call it? Per Alexanderson. Per Alexanderson. Thanks for coming. Per, do you know the cardinality of the set of real numbers? You can unmute yourself for a second. Okay. Vincius, do you know the cardinality of set of real numbers? If not, I'll tell you. Okay, does anybody know?
Per Alexanderson answered in the comments, continuum.
Okay, what do you say? Okay,
Continuum.
very good. Oh, very good. Yes. So the probability that a random probability that gamma, or for that matter, zeta 5 or any is rational, is a quotient of Aleph 0, which is a big number, divided by an even bigger number. And this is so infinitesimal. So for me, this is very, very small zero. So that's why it would be a nice intellectual exercise to prove rigorously that gamma or any of the still wide open problem. For example, E plus pi is still, you'll be famous if you can prove E is irrational, goes back to Euler, it's a simple exercise. That pi is irrational goes back to Lambert 270 years ago. But nobody can prove rigorously, although I'm sure it's true, that E plus pi is a rational number. Nobody can prove rigorously that E times pi is a rational number, let alone transcendental. Nobody can prove. Tells you how little we can prove. Exercise, they cannot both be rational. At least one of them is rigorously. But of course, both of them are irrational. Finally, I also promise you about Goldbach conjecture. Once again, it's a probabilistic proof that have a little macro. So reminding you, Goldbach conjecture says that every even integer bigger than 2 can be written as a sum of 2 primes. Let's have a little macro for Goldbach, proc n. So I want to find the set of all primes. So you input a positive integer n and the set of all primes such that 2n minus p is also a prime. So let's do it empirically, experimentally. So I start with p as the first prime. Sorry. And then I collect. I start with the empty set. And while p is less than n, do the following. If Maple has a command called is prime, 2n minus p, 2n minus p. So then make you make it part of S. You include it as. And now we have to make P the next guy, next prime. Let's make a comment. D And the output, it tells you not just whether or not it's possible, but it tells you exactly how many ways you can write 2n as a sum of primes. So let's do G of 10. It's not empty. The Goldbach conjecture says it's never empty. But not only is it not empty, what's probably true, that the number of elements, the relative frequency of this, oops, sorry, the digit is too big. Let me make digits back to 10. Sorry. Is this, and you can do 5,000. So it's a good, hefty, and by the prime number theorem, the percentage of primes is 1 over log. But now we have two things have to be primes. So heuristically, but completely safe, this is roughly, and there's a clear heuristic that may go back to Hardy, I forgot the name, that gives heuristic estimate for the constants. It's not exactly a 1 over log n square, but it's some constant. And this is so convincing to me that not only it's a non-empty set, but it grows like roughly a constant of n over log n square. So it grows very, very fast. Finally, the punchline is a P versus NP. And this is not due to me again. It's due to a good friend of my good friend, Niels Sloan, one of the greatest people who lived in the 20th century of all time, Claude Shannon. And Neil edited the collected work of Shannon, and I love to browse in them. So it's still nice to have, can you see the book? Okay, let me stop sharing for a second. How to stop sharing? Okay, anyway, here, it may cost $200, but it was every page of this. It's really collected papers of Claude Shannon. So Shannon is my great hero. And in his master thesis, he did one of the greatest, one of possibly the most significant master thesis ever. He introduced the notion of a Boolean circuit. So you have the input, and then you go to the shop, the electric shop, and you have gates. You have AND gates, OR gates, and NOT gate. The NOT gates are very cheap, they cost 0. But AND gate and OR gate, they cost something. And you start with the input gates, and then you build the circuit. The next level, for example, X1 and NX2. By the way, if there's no not, if not allowed, it's called a monotone circuit. And it computes so-called monotone Boolean functions. So, for example, AND, X1, and not, and so on. So it's a very complicated thing, blah, blah, blah. And at the bottom, after many, many things, so every gate has two parents, the incoming. So it's like a directed graph with no cycles. And at the end, you have the output files. As is obvious in hindsight, but Shannon proved or illustrated, every Boolean function can be represented by such a Boolean circuit. The easiest way, you take the either conjunctive normal form or disjunctive normal form, and then you can easily construct one. But what Shannon proved. Another way that is better for computation and conceptually is what's called straight line program. Since it's an undirected graph, so you put the inputs first, the first n lines are the inputs, and then every new line is the logical gate, which is 10 of them, 10 non-trivial Boolean functions. So the Boolean function in B2, some function, one of the 10 functions of 2 variables that are non-trivial, that are generally 2 functions, and 2 parents. And the Boolean, the P versus NP problem is equivalent. It's easy to see. You don't have to talk about Turing machines and all that requires lots of background. This you can explain to a 5-year-old about Boolean circuits, about end and or. It's very, very intuitive that the so-called size of such a Boolean circuit, or equivalently a straight line program, for one of the many NP hard problems, can never be of polynomial size. It has to be exponential size, or at least super polynomial. And Razbarov got famous and got improved by Alon and Bopana for the case of monotone circuits, but not the function negation is not allowed, then it's true. But it's still wide open to have a rigorous proof. But Claude Shannon, my great hero, proved it, and the proof, once again, is probabilistic. Look at very, very gross upper bound for the number of straight line programs with polynomial number gates. So how many gates are there? Paul n. Each of them has 2 parents, Paul square. Now you have to decide for each of them, decide who are your parents, and a lot of this will be nonsense and lots will be redundant. There's only a very crude upper bound. So it looks like a very big number, a polynomial to the power polynomial square times, and for each of them decide which of the 10 a Boolean function of 2 variables. So you have 10 to the power. Look like a big number. But this is peanuts, peanuts, nothing compared to the total number of Boolean function. Exercise for you, that as n goes to infinity, the ratio of this to this goes to 0. Hint, take log. The log of this is polynomial. The log of this is exponential. So all these functions, all these famous functions, the P versus NP, time it up. Thank you. This ends this talk. Thanks so much for coming. If you want to have any questions, feel free to write me email.